right, good morning. So right now I'm going to be going over the electricity or electrostatics practice test. I'm first going to be showing you the physics formula sheet on how I laid it out. So if we go down to fields, this is kind of the squared boxes are kind of the electricity unit. There's also this one here, which you can use as well. But I think these are the main ones. So we have a force. The force applied to some charge is K, the charge of the two over the distance between them squared. We have the field, which is this force that is applied to the test charge divided by the test charge to get newtons per coulomb. And then it also can be represented as this one, where it's the source charge over r squared times k. And then we also have potential energy over here, which is the same as the force, except it's just divided by r, not r squared here this time. So potential energy, it's just based on the two charges and the distance between them. In this equation, it is important to make sure you have the signs in, because it depends on definitely on their signs. And then it's also equal to the test charge times the electric field times the distance from the source charge. Okay, so that's another thing you can add in. And then we have voltage, which is potential, which is known as K times the source charge divided by R. Okay, and that gets you joules per coulomb. Okay, the amount of energy it takes per coulomb to get from infinity to there. Okay, so that can be a positive amount or a negative amount. Say if you have a positive and a negative, it wants to go from infinity to your spot, so it's going to end up being a negative value because you don't have to do any work to get there. And here we have potential difference, which is pretty much the same thing. Generally, we usually only work in potential difference rather than just potential, because all potential differences is you just take it in one spot and you minus it from another spot. So here it's the change in potential energy between the two spots divided by the test charge. Alright, so those are all the formulas that we're going to be using. So let's try to do the practice test. A proton is placed in an electric field of strength 5 times 10 to the 3 newtons per coulomb. At what rate will it accelerate? Proton mass they give you and the proton charge they give you. You can see the mass is way smaller than even the charge. Alright, so our electric field is 5,000 everywhere it's assuming, and then we have the two values here. Alright, so when I see this, I see an energy or an electric field value, so I know I'm going to have to use that. So I go back to my formula sheet. So I see this one here. Do they give us a force? Not really. Do they give us a test charge amount? Yeah, the proton charge here. Okay, so they give us an E and a QT value, so we can use this formula here. So we're going to go E equals FQ over QT. And then we can solve for F. FQ, we just multiply by this QT, E times QT, and we end up getting our electric field value, which is 5,000 newtons per coulomb, and the test charge, which is 1.6 e to the negative 19. If they don't give you the test charge, you can look at the back of the formula sheet, and it's this elementary charge here. It's a little bit different, but close enough. And then we can calculate in our calculator, and I get 8 times 10 to the negative 16 newtons as our force here. So very small force is being applied to this very small proton. So now we want to know acceleration though. Force is also mass times acceleration, we know that. So our force is also mass times acceleration. So we want to find out acceleration, we can solve for A. which is F divided by M. Our force is 8 e to the negative 16, and our mass is this tiny amount, 1.67 e to the negative 27. And then when I plug this in my calculator, I get an acceleration value of 4.79 e to the 11 meters per second squared, which is a really high acceleration value. If you notice, the speed of light is 3 e to the 8 meters per second. But this is an acceleration value which is not really correlated with that speed value. You'd be like, oh, it's faster than the speed of light, but no, it's not really the speed value, it's an acceleration value. So that's okay, it just means it's accelerating really fast. So that's our answer there. Okay, question 2, here's kind of a more understanding question. What is the difference between force, which is variable F, and field strength, which is variable E, in electrostatics? So generally when I get a contrast question, I just try to define them both and then see what the difference is. So what is force? Force is kind of the force felt at a spot relative to a source charge. Okay, so force is the overall force felt relative to a source charge. It also depends on what the test charge is, because if you have more coulombs, it's going to feel more force. Okay, relative to a source charge. So it's the force felt of some sphere at a particular spot. Okay, and it generally is compared to some other bigger source charge. What is the field strength? Field strength is really similar. It's the force felt at a spot as well, but this time it's per coulomb of test charge. Okay, so similar to gravity, this force felt would be the force of gravity, and the field strength would be the force of gravity per kilogram. So this one's the force felt per coulomb of test charge. Okay, so they're really similar. You can get from this one to this one just by multiplying how many coulombs the test charge has. Alright, question 3. Here's a field question. The electric field strength at a distance of 1 meter from the point charge is 40,000 newtons per coulomb. Okay, so the electric field strength, say here from this one, is 40,000 newtons per coulomb of that this test charge has from this spot. What will the electric field strength be at a distance of 2 meters? Okay, so say they're both positive and then this one moves from there to there. So you can guess that the electric field strength, or the force it's going to feel, is going to be, I'm going to guess, less as it's further away, right? Because it would be repelled less. So let's try to find this. We're going to try to find E, which is electric field strength, which is, we know, is force over test charge. We don't have a force or a test charge value, but we also know that it can be K source charge divided by R squared. Alright, so this is the electric field value. So it's going to be K. We don't know what the source charge is, so I'm just going to go source charge divided by R squared, which is just 1 here. So overall, our 40,000 newtons per coulomb value is just going to be equal to K times QS. So we can find out what the source charge is, if we want to, we could solve for that. We could plug 40,000 in there, plug in our K value, divide by the K value, and we get our source charge. But I don't quite need to do that. I just need to know that it's going to be K times whatever the source charge is going to be. And then let's try to find it down here. Our energy value here is going to be F over QT. But again, we don't have the value, so we're going to use the F or the KQS over R squared one. And it's going to be K, this source charge again, because that doesn't change, over this time 2 squared. And this is going to be KQS over 4. So if we look at the two equations, they're going to be the same thing. This is just going to be a fourth as much. Okay, so if this value is 40,000 newtons per coulomb, this one's going to be a fourth as much. So overall, I know energy, we'll just say, or electric field at spot 2 is just going to be electric field at spot 1 times a quarter. So it's going to end up being 10,000 newtons per coulomb. Okay. This question you could also do by solving for QS, plugging it in there, and then you'd see that it would be 10,000 as well. That would work as well, and it might make more sense for you. Alright, question 4. Calculate the electrostatic force. We need a force value of attraction, so that means one must be positive and one must be negative when they are 0.3 meters apart. So here, when I look at this, we're going to have to find a force. We have two charges and the distance between them, so I know I can just use this equation. When I plug in 80 to the negative 6, 5e to the negative 6, and r, which is 0.3 squared, I end up getting 3.995 newtons of force of attraction. Okay, so they're both feeling that force going towards each other. All right, question 5. Two parallel plates are 4 millimeters apart. This is, you gotta be careful, 4 millimeters, not centimeters or not meters, which is going to be 0.004 meters. And then it has this potential difference, which is very confusing, but it's the joules of Coulomb to get from one spot to the other. So if you have 1 Coulomb of test charge and you want to bring it from here to here, it would take 200 joules of energy. That's what it means. What is the magnitude of the electric field strength between the plates? So what is the electric field strength? We need to find out what variable E is. Okay. All right, so in this question, I know I have the volts, so I'm going to probably have to use that equation. So the change in volts from here, this spot to this spot is 200. So what's the equation for change in volts? It's change in the potential energy over whatever test charge you have, because it's joules per coulomb. And then if we plug in the potential energy formula, QT times E times R for potential energy, we notice that those cancel out, and we get, I can't get rid of the change, we get this here. So now we're at change in V is equal to the change in E times R. Alright, so if you notice, the electric field between two plates does not change. So this can also be seen as whatever E is going to be times the change in R. Okay, so the change in R we know is just going to be the difference between the two plates, which is 0.004 meters. So overall, our formula is change in V times E times delta R. Let's plug in our values. The change in the volts is 200 joules per coulomb, and our electricity field strength is what we're trying to find, and our change in R is 0.004 meters. Divide by this and we get an E value of 50, no, one too many zeros, 50,000 newtons per coulomb. So the electric field strength that it would feel is 50,000 newtons of force per coulomb at any spot in between these two plates. All right, question 6. What is the electric potential relative to infinity of an electron that is 5.3 e to the negative 11 meters from the proton? So this is relative to infinity, so it's going from infinity to this spot, is what it means. So what is the electric potential, which we know is V, the variable V, relative to infinity? So here, we know V is going to be, usually you use the change in V, which is the change in potential energy over QT. And the interesting thing here is you're going from infinity to this spot, so it's from spot 1 to spot 2. And the one thing you know about infinity, no matter what the sign of the charges are, it's always going to be potential energy of 0. So it's the difference from 0 to whatever this is. Okay, so you don't really have to worry about the change in, because you know that one of them is just going to be 0. So it's going to end up being potential energy over QT without the triangle. And do we have any potential energy values or Q charges? Yeah, we have a test charge, but do we have a potential energy value? We don't. So we're going to use the other formula for volts, which is K Q source charge over the distance between them, because we know we have a distance between them. So this is going to be your K constant times the source charge, which is 1.602 e to the negative 19 over the distance between them, which is 5.3 e to the negative 11. And what this is going to give me is 27.17 volts or joules per coulomb. So it's going to take 27.17 joules to get from infinity to this spot per coulomb of charge you have. So this is not, I would say not too much joules to go from a spot which is infinity away all the way to here, which is pretty close to this one. But if you notice, the coulomb charges are so tiny. All right. So overall, if we want to know, or that's our answer, but one thing you have to notice is that this electron wants to go towards this proton. So really, to go from infinity to this spot, you don't have to put any amount of joules in it. It's going to do it on its own. So if it's going to do it on its own, it has to be a negative value. It's going to take negative 27.17 joules of work per coulomb to get from infinity to there. It's going to do it on its own. You're actually going to get work out of it. All right. So that's the answer for that one. And now we're on the last one. This one's a bit longer one. It's a three-part question. There are three charges, A, B, and C. What is the overall force felt from A? So here we have A here, we have B here, and we have C here, and we have distances between the two. Okay, so they're all a positive charge. So you know this one's going to put a force that way, and this one's going to put a force that way on A. Okay, and they're also going to put a force on each other, but we're not going to worry about that. All right, what is the overall force felt from A? Well, let's calculate it. First, the force, we'll say, of A from B, which is K, QA, QB over R squared, which is going to be 11,556 newtons when I plug in 9e to the negative 5, 7e to the negative 5, and the distance between them, 0.07 meters squared. So that's the number you should get. And then we have F of A and C this time is going to be K QA again, but this time QC over R squared. So now instead of plugging in the 7e to the negative 5, we're going to plug in 9e to the negative 6 for your QC. And then your R is going to be 0.04 instead of 0.07 this time. So that time, or this time we get 4,550 newtons, which makes sense because this is a much smaller coulomb amount. Okay, so it's going to feel this one to the left, this one up. So now we have our two values. We can't just add them together though, because they're not in the same direction. So we're going to go A, draw a little separate picture, is going to feel a force this direction from B. which we calculated to be 11,556. And then it's going to also feel a force up from C, which is 4,550. And then we just want to find our overall net vector. The camera, sorry. And we also need to know at what angle it's going to go at. So if we want to find out an angle, let's do that. Tan inverse of O over A. And that's going to give me 21.5 degrees, as that angle is what direction it's going to go at. And then we also have to find the net force, or F net. In this case, it's going to be Pythagoras, so it's going to be the square root of this squared plus this squared. And that's going to give me 12,419 newtons. Okay, so overall it's going to feel a little more than this one. 12,419 newtons in a direction of 21.5 degrees above the horizontal. So it's going to go that way. Alright, so we did the first one, force. Now the second part, what is the potential energy required to bring it from infinity to A? So here we go, note 2. Let's just look at it in different parts. So you're going to bring infinity to here in respect to B, and also infinity to here in respect to C. So we're going to do them in just two different cases. So we'll go potential energy in respect to B. So we're only going to look at B. We know potential energy is just K times the charge of A times the charge of B over R this time, not R squared. Okay, the distance between them. So very similar to our last one. If we plug in all our values, you should get 808.9 joules of energy to bring that charge to that spot from B. Now we're going to look at potential energy in respect to C, and it's going to be the same thing, just times QC, and the R value will be different. It'll be 4 centimeters instead of the 7 centimeters. So this time I get 182.0 joules to get from infinity to the same spot but in respect to C. So it takes less energy to get there. So overall we want the total, which is going to be potential energy at spot B plus potential energy at spot C, which is going to be 808.9 plus 882, or 990.9 joules of energy to get to spot A when both B and C are there. Alright, so that one's done. Now let's do the third part. What is the electric potential difference between infinity and A? Okay, so again, this is the potential energy divided by your source charge. Okay, so if we recall, potential energy at the infinity spot is 0. So if we want the potential voltage difference, it's just going to be the same as the volts at A, because the volt at infinity is 0. So the volt at A is just going to be potential energy to get to spot A divided by your charge of A. And this is just going to be our 990.9 joules to get there, divided by how much charge A has, which is a small amount, 9e to the negative 5 coulombs. And then when we calculate that, I get 11,010,078 volts, or joules per coulomb. I like writing joules per coulomb because it makes more sense to me. So it takes 11 million joules to move a coulomb to that spot from infinity. Okay, so you can tell it's a lot higher than our 990, but that's because 1 coulomb is a lot more than 9e to the negative 5. And there's the practice test. Thanks.